Now, let's start with the definition of thermal strain. Just imagine the deformation of a bar exposed to the increasing of temperature. We assume that the temperature has increased by delta T. The thermal strain is the strain caused by the increase of temperature delta T. Then, we noted that the original length of the bar, which is L0, has become L due to the rise of the temperature. This is the equation that defines the thermal strain. So, deducting L0, original length, from L, final length, results in the elongation delta L. The delta L is the elongation due to the increase of temperature. Then, we define the thermal strain as the ratio of the elongation delta L to the original length L. The point is that this strain is caused by the temperature change. So, we need to define the relationship between thermal strain and temperature. The relationship is given by the following equation. You may notice what the equation means. The thermal strain on the left is proportional to the temperature change. This equation does not say that the strain is proportional to temperature, but proportional to the temperature change relative to the reference temperature. So, delta T is the amount of change. The equation defines the thermal strain as a product of a change in temperature and a coefficient. Here, the proportional constant alpha, which associates delta T with thermal strain, is the coefficient between thermal strain and temperature change, which is called linear coefficient of thermal expansion. Some of you may be tempted to call this coefficient just a coefficient of thermal expansion, because this coefficient is related to thermal expansion. In fact, there is another coefficient that is called coefficient of thermal expansion. The coefficient defines the volume. In the field of mechanical engineering and aerospace engineering, linear coefficient of thermal expansion is used more often. So, you should first understand distinguishing these two coefficients. As you can see from the equation, strain epsilon is a dimensionless value. For example, if this value is 0.1, it means 10% of elongation. This is what the word dimensionless means. On the other hand, on the right of the equation includes delta T, temperature change. Considering its unit is Kelvin, the linear coefficient of thermal expansion alpha is given with the unit of 1 over Kelvin. As mentioned before, the unit of temperature is normally Kelvin in engineering fields. Sometimes, in exercises, temperature change from one temperature to another may be given in the form of Celsius temperature. But no problem exists here, as far as considering the value of temperature changes. Anyway, you should be noted that the unit of temperature change is Kelvin, and the unit of linear coefficient of thermal expansion is 1 over Kelvin. Following the definition of thermal strain, we are now arguing about how much materials are deformed due to temperature changes with respect to the table. As an example, let's consider carbon steels. Mild steel, which was introduced before, is a type of carbon steels. The linear coefficient of thermal expansion of carbon steel is about 11 micro per Kelvin. Micro means minus 6 power of 10, 1 over 1 million, with 6 zeros. A material deforms this much at every 1 Kelvin. To be more specific, we may assume a bar of 1 meter long and the temperature rises by 1 degree Celsius. Then the bar becomes longer by 11 micrometers. Here, you should be clear with these units. You may recognize the value of 11 micrometers is very small. It is true that the elongation is small when the temperature changes only by 1 degree. But when the temperature changes by 10 degrees or 100 degrees, the thermal strain is so large that we cannot ignore. Again, the linear coefficient of thermal expansion is usually measured in units of 1 lower Kelvin, which is the unit of strain per unit temperature change. Strain is usually expressed in micro, so you may sometimes see the notation of micro per Kelvin, or you can write down the part of micro as multiplied 10 to the minus 6 per Kelvin. In any case, the value of carbon steel is about 11 micro per Kelvin. Copper is a little larger than this. In addition, aluminum alloy is about 24 micro per Kelvin. It means that carbon steel expands less than aluminum alloy. Here, you may consider a piece of carbon steel and aluminum bonded together. At room temperature, it is flat. However, if you raise the temperature, the aluminum part expands more than the carbon steel part. Then, it behaves as if it is slightly bent or deformed toward the carbon steel. You may remember that materials with different linear coefficients of thermal expansion can be deformed as this piece when the temperature changes. Next, we are going to consider polycarbonate and epoxy resin at the bottom of this list. Polycarbonate is a thermoplastic resin. Thermoplastic resins soften and melt when the temperature is raised. And when you bring the temperature back to room temperature, they solidify again and become a solid object. PETs used for plastic bottles also have such characteristics. The linear coefficients of thermal expansion of polycarbonates are about 70 micro per Kelvin. Epoxy resins are thermosetting resins. An obvious example of an epoxy resin is glues. When a glue of epoxy resin is poured, it hardens after a certain interval of time. Then, materials can be stuck together. When you raise the temperature, it does melt and become soft. Once it has hardened, it stays hard. Glues harden at room temperature. Normally, resins that are used as structure materials are hardened by raising temperature. Once such resins are hardened by heat, it stays hard. This phenomenon is called thermosetting. Then, such resins that are irreversibly hardened are called thermosetting resins. Many of the resins that compose these composite materials, which are used in airplanes, for example, are also epoxy resins. The linear coefficients of thermal expansion are roughly 40 to 80 for epoxy resins. They vary in this range, but keep in mind that the linear coefficients of thermal expansion for resins can be in dozens.